We're in agreement that 5 to the 0 is equal to 1, but the big question is why?
I said something like 5 raised to the 3rd power. We call this the exponent form.
And we can also write that in expanded form. And we talked about yesterday that this means that I'm going to write the number 5 3 times.
So this is going to look like 5 times 5 times 5.
And yeah, we can do the math for that. 5 times 5 times 5 is 125.
We call this like the evaluated form and the expanded form.
I'm throwing out some vocabulary, but I don't really expect you to know about the vocabulary, and I'm very rarely going to ask you in those terms. So here's the thing. If that's true, and I take something like, let's say 5, I'm going to use another notation here. It's kind of old school notation, but caret notation. If I write 5 caret 2, that's how we would read that. This is the same thing as writing 5 squared, just another notation. This is a notation that we're often using like when we're typing answers into some sort of online program, or when we're lazy and we're typing fast. That's easier than hitting the shortcut key to give yourself a superscript, right? So if I had 5 squared and I multiplied that by, let's say 5 to the 4th. Well, if I took this whole thing and I wanted to write it out in its expanded form, this says 5 times 5, and then we would be multiplying that by 5 times 5 times 5 times 5. Well, at the end of the day, how many 5s do I have? I have 6 of them. So that's the same as 5 raised to the 6th power. What the additive law of exponents says is the shortcut way to get to the 5 to the 6th would be to say that this is 5 raised to the 2 plus 4. Now, the truth is that in terms of exponent rules, this is the one thing that a bunch of now dead mathematicians agreed on, right? Most of math is kind of arbitrary rules that a group of people decided on. But mathematicians try to be efficient. So they tried to make as few rules as possible, and then everything else has to follow from that. So our additive law of exponents, if we wrote it out in like the most general terms, our additive law of exponents would say that if I had, I'll use letters, but if I had something like b raised to the a power times b raised to the c power, that's the same as b raised to the a plus c. That's what our additive law of exponents says. Okay, I promise I'm going somewhere with this 0 thing. Well, if that's what our additive law of exponents says, then if I wrote, let's say 7 raised to the 0 power times 7 raised to the 2nd power, well, the additive law of exponents means this would have to be equal to 7 raised to the 0 plus 2. Well, for the time being, let's pretend I don't know what 7 to the 0 is. Well, then this statement says whatever goes in this box has to make this thing true. Something times, well, 7 squared is 49. So something times 49 would have to equal 7 to the 0 plus 2. That's the same as 7 squared. So that is another 49. So we don't have a choice. 7 raised to the 0 has to be equal to 1. Not because your high school math teacher told you that, not because your 7th grade math teacher told you that, but because mathematicians decided that the additive law of exponents was the one rule they were going to agree on. 5 to the second power times 5 to the negative 2. Now remember, the only law we've got to work with so far is that additive law of exponents. So we know what 5 squared is because that we can write in the expanded form. I can write that as 5 times 5. But if I didn't know what 5 to the negative 2 was, it was kind of this thing that I was trying to figure out. The additive law of exponents says that when I multiply those two things together, because they have the same base, they have the same number in the base, that's going to look like 5 to the 2 plus negative 2. Well, 2 plus negative 2 is 5 to the 0. So right now, I'm looking at 5 times 5, which is 25, times this mystery number that we don't know what it is yet. And 5 to the 0, we just figured out is equal to 1, which means there's actually really only one choice for what goes in that box. It has to be 1 over 25. Now, my guess is that very few of you were taught about negative exponents based on the additive law of exponents. But that's where this comes from. So it's not an arbitrary rule. The only rule mathematicians decided on was this one up top. Everything else is just a consequence of it. So what that tells me is kind of the shortcut way to work with that. If I write 5 raised to the negative 2, there are a couple of ways that we can think about that. I choose to just go straight to calling that a fraction. And this is equivalent to saying 1 divided by 5 squared. You could also go straight, because the numbers aren't too bad, to writing that as 1 over 25. Really up to you. You rate, if I had b to the m divided by b to the n, shortcut wise, this is just going to become b to the m minus n. Now there's all kinds of ways to get there. Again, thinking about if I only had the additive law of exponents to work with, then we could choose to rewrite this. And let's do it with some concrete numbers. So if this said 5 to the 3rd power divided by 5 to the 7th power, I could choose to rewrite that as 5 to the 3rd power times 1 divided by 5 to the 7th power, which we know from our negative exponent property. I could then rewrite that to say 5 to the 3rd power times 5 to the negative 7 power. And then using the additive law of exponents, I could write that as 5 to the 3 plus negative 7. And then if we did the math there, we'd end up with 5 to the negative 4th. Nobody's going to do all that. I should have told y'all not to write it. Nobody's going to do all that. But you are going to find which of those ways of writing this makes the most sense in your head. And then you're going to choose the path that's right for you. So I mentioned this yesterday. Unfortunately, there are a lot of right ways to get the right answer in math. And sometimes it's uncomfortable, but you have choices. One of our kind of underlying goals in the background for Math D is to help us get a little bit faster at recognizing where you personally are comfortable taking the shortcut. So if you look at 5 to the 3rd over 5 to the 7th, and it feels comfortable to go straight to 5 to the negative 4, that's what I want you to do. If right now that doesn't feel comfortable yet and you want to play around with different ways to write it first, go for it. Other options, if that doesn't feel comfortable either, you can take that 5 to the 3rd over 5 to the 7th and write everything out in expanded form. Now, this is a heck of a lot of writing. I do not write that fast. If I were in a class taking a timed exam, I do not have time to do this. And then go through and think about, well, that's a 1, that's a 1, that's a 1, that's 1 over 5 to the 4th. But what is important, especially for a multiple choice exam like the placement test, or even if you're just trying to check your answers with the back of the textbook, is to understand that all of these are equivalent ways to write the same thing. Had something that looked like b raised to the m power raised to the n power. And to make that a little bit more concrete, if I were doing that with some numbers, maybe I would have 5 to the 3rd squared. I must have changed my angle a little bit because I got a bunch of glare on the board. There we go. 5 to the 3rd squared. So thinking about how exponents work, this whole thing in parentheses, that's my base, and it's being squared. Well, being squared means I'm going to take the whole thing, write it over again twice. So this, if I were writing that in its expanded form, would look like 5 cubed times 5 cubed. And now I can apply that additive law of exponents, which would make that 5 to the 3 plus 3. And repeated addition, the same as multiplication, which means the shortcut way to get here was to just write this as 5 to the 3 times 2. Or if I'm putting it more generically, that's going to look like b to the m times n. A times b raised to the m power. And let me make that a little more concrete. Let's think about it with numbers. So if I had 5 times 2 raised to the 4th power, then thinking about what this means as an expanded form, this would say 5 times 2 times 5 times 2 times 5 times 2 times 5 times 2. So if I kind of rearrange those, because everything is multiplication and multiplication of numbers is commutative, meaning you can change the order that you do the multiplication in, I can regroup these so that I've got 4 of those 5s together and 4 of those 2s together, which means that our distributive property is essentially that we can distribute that exponent in. So this would look like a to the m times b to the m. Now I'm going to pause for a second because the number one place where calculus students make mistakes on this, I just want to point out, the number one place where calculus students make mistakes on this is the difference between writing something like 5x cubed to the 4th. So this right here, number one mistake that I'm going to see is 5x to the 12th. But what this means notation-wise, if I were to write this in expanded form, that says I have 5x cubed times 5x cubed times 5x cubed times 5x cubed, meaning I've got 5 to the 4th in addition to that x to the 12th. We talked about this yesterday, but for the sake of folks that have just joined us, UC Davis is pretty much a non-calculator campus in terms of calculus and other math classes. But the good news is that means you wouldn't be expected to calculate this out. You could just walk away and leave that written as 5 to the 4th times x to the 12th. In Math D, If numbers are going to add to your stress in any way, please pick up a calculator, throw that into a calculator, because I want you focused on the algebra piece of it, not stumbling around on the numbers. So for this class, the focus is the algebra. Deal with the numbers however you personally need to deal with the numbers. Okay. Since we're talking about the distributive property, I'm just going to add one more thing here and say that if I had -3 squared, and this is purely a notation thing. This is, mathematicians had to agree on some notation. This, notation-wise, is not the same as -3 squared. This, notation-wise, thinking about the order of operations, which some people think about as PEMDAS, parentheses, exponents, multiplication and division, addition and subtraction. If we're looking at this, technically we have to deal with the exponent first, which means this would take the 3 and square it and get 9, and then we'd make that negative. This one, we would use our exponent properties to say this is in its expanded form, -3 times -3. And -3 times -3 would end up with a +9. So I would say of all the exponent rules that people mess up the most when they're doing calculus problems, it is for sure this one. This is the same as a raised to the m divided by b raised to the m. Now, I would say the place where, again, this same rule, the same distributive property trips students up when they're working through calculus problems is if we had something like, let's say x squared over 4 to the third, or 1/4 x squared cubed. And I'd say the mistake happens more often when it's written like this, even though these two things mean the same thing. I think when we write the fraction like this, it's a little bit easier. Your brain, your visual processor, I think has an easier time of seeing this one as x squared cubed over 4 cubed. And this one, brains tend to cube that x squared and think, oh, that coefficient out in front should still be a 1/4. But this should also look like 1/4 cubed times x squared cubed. On Thursday, we're going to be talking about factoring. We're going to talk about polynomials and factoring. And the bottom line is, if you're really good at multiplication facts and really good at your addition facts, let's say for adding any combination or multiplying any combination of numbers 1 to 12, it really helps with factoring. So I don't know if any of you all, when you were in elementary school, did those like mad minute things. I don't know if that's a thing anymore. But I'm going to post some mad minutes because I'm not kidding. If you're like super quick with your multiplication facts and your addition facts, it really, really super helps with factoring. So I'm just making a quick plug for that. Now, the other thing I'm going to say in terms of exponents. So it is true that in general, you don't have to simplify your answers in calculus if we're not using a calculator. But there are a lot of problems where the instructor who's written the problem thinks that they've given you nice numbers. So I just want to kind of quickly make a list in terms of exponents of what numbers you should actually get familiar with and memorize, because they show up often enough that, again, it's about getting a little bit faster with stuff. So I'm going to do something really dumb. Don't write this first one, but 1 squared is 1. I bet y'all knew that. And 1 cubed is also 1, and 1 to the 4th is also 1. I'm not going to keep writing, but if this is one that your brain should just look at and immediately not even think about. 1 raised to some power is going to be 1. Powers of 2, I think you ought to be able to do powers of 2 in your head at least to 2 to the 5th. You should be kind of on that commit it to memory list. For powers of 3, I think you ought to be able to do 3 squared, 3 cubed, and 3 to the 4th, because all of those numbers come up a lot in textbook problems. For 4s, I want us to be able to get to 4 cubed. For 5s, I'm going to go 5 cubed. And for anything bigger than that, probably just the number squared. A question came up in the chat while we were on break, and I definitely want to address it before we move on to talk about monomials. I know my camera's blurry. I'm going to give it a second to find itself. Okay, it did. Awesome. So the question was, all the examples I did had things with the same base being multiplied together. Well, what if they're not the same base? And that's a really good question. So that would look like maybe having, let's say I had 5 to the 3rd times 6 squared. So these two exponents this has a base of 5 and an exponent of 3, a base of 6 and an exponent of 2. Well, if I were to expand this out, that would look like 5 times 5 times 5, and that would look like 6 times 6. There isn't really a way for me to put these together. So there isn't anything I can do with this. We got to just walk away. Or if you want, we can work the numbers out, right? The 5 cubed part would be 125, and the 6 squared part would be 36. I don't want to confuse anyone with this next part. My recommendation at this moment, don't write it down, just watch. We can do something if they don't have the same base, but they do have the same exponent. So if I had 5 to the 4th times 6 to the 4th, I can use that distributive property in reverse to say they have the same exponent. So I could group that together as 5 times 6 to the 4th and write that as 30 raised to the 4th. And that probably would be a more simplified form. I will also say, if I had to actually do this without a calculator, that's not what I would do. If I had to do this without a calculator, I might get here, but then break that back down to say 3 times 10 to the 4th and reuse that distributive property to say 3 to the 4th times 10 to the 4th. 3 to the 4th, that's one of those numbers we're going to get memorized. So that would be 81. And 10 to the 4th, the nice thing about powers of 10 is we just put in that many zeros. So, which means if I put that all together, I would have 810,000. Now, I said you didn't need to take notes. I'm not really expecting anyone to be doing this. I will say that if you are sitting in class and it seems like the person sitting next to you is just that much smarter, they're not. Being able to manipulate things like this quickly in your head makes you look a lot smarter in calculus or pre-calculus. But writing it out by hand is the same thing. But this really being able to see how to get through the numbers faster in your head is usually the difference between the students who can do stuff really fast and it looks like they're just getting it really fast. It's usually because they're good with numbers. And I don't have a cure for that other than do some of those mad minutes, get a little bit faster with your number sense. And the algebra will start to feel faster too. Okay, I'm going to erase this stuff and move on to talk about monomials. Some of you I know are various forms of biology majors, which means eventually you'll probably take Classics 30, which is a word roots class. But a lot of times you've already seen some of these word roots popping up maybe in high school biology, or maybe you had an English teacher who cared about word roots. I don't care a ton about word roots, but they show up in a lot of our terms, both in math and in science. So monomials, that mono piece, just means one. So monomials are anything that looks like a constant. That's technically a monomial. 3 or 47, right? These are just constants. But a monomial is also anything that's a multiplied together combination of constants and variables raised to whole number powers. So if I said 3x squared, that's technically a monomial too, because this thing is kind of all one piece together. I could even have something like 10x cubed y to the 4th. That is also a monomial because it's one group of things together, all multiplied. I can have constants and variables to whole numbers. So all of these are examples of monomials. Homework B has a lot of mess around with these monomials and apply all of the exponent laws to them. And we've done a little bit of that so far, but not a lot of it. So let's just get some practice using those exponent rules when it comes to monomials. So let's say, just kind of another pro tip. The instructions in algebra textbooks are terrible. That'll be like a whole set of problems that says simplify. That's a little vague. Multiply, also a little vague, right? But those are the words that we're kind of stuck with when we're reading textbooks, and those are the words that we're stuck with when we're doing problems on that lovely placement exam you'll all be taking again. So if I give the instruction multiply, and we're thinking about maybe something that looks like 3x squared times 4y. Sorry, let me make them both. Yeah, there we go. 4y cubed x. And I ask you to multiply this. That means that we're going to do whatever multiplication and apply whatever exponent rules we need to make this in its most simplified monomial form. So for starters, because everything's being multiplied together, I don't actually need to write the parentheses. If there were addition in between here, then those parentheses would be needed. But because it's all multiplication, I can ditch the parentheses and just group my like terms together. So I'm going to go ahead and multiply the 3 times the 4. And then if I were just writing the rest of this out, I'd have x squared and a y cubed and an x, but I'm going to group those x's together. And again, The invisible exponent on this x is a 1. So when I use the additive law of exponents here, I'd end up with 12. X, 2 plus 1 would give me 3, y cubed. This is just a convention. It's not a rule. The mathematical convention, meaning the way it's going to be written most of the time in textbooks, is when we're writing a monomial to use the variables in alphabetical order. That's just the convention. But this is absolutely equivalent to writing 12y cubed x to the third. In fact, it's also equivalent to writing x squared 12y cubed. However, this version of it is almost never written. And I think it's just because, I don't know, maybe it's too easy for the number to get lost in there. But we almost always, like very rare exceptions, even if that's what I might write just because of the order that things were written in, I would immediately switch it around to this for my final answer. But they're all technically equivalent. So just something to keep an eye out for, especially as you're doing like multiple choice problems. Maybe this is what you got, but that's what it looks like in the book. So just make sure that you kind of have that on your radar. Now we'll talk about other kinds of division shortly. Probably by next week, we'll be talking about other kinds of division. But for now, if we're talking specifically about monomials and our instructions are to divide, we're talking about the same kind of thing that we were with multiplication. Meaning if I have 10x cubed y squared divided by 5xy to the 10th, then divide means I'm going to apply exponent laws to each of our like or similar terms. So personally, I start off with the numbers. So 10 divided by 5, I can simplify, make that a 2. X cubed divided by x. Again, that x living by itself has an invisible exponent of 1. You can choose to rewrite this, bringing the x and the 10 up to the top and changing their exponents to be negative. Or we can just do the subtraction thing. Those x's have the same base. So using our exponent laws, that's going to become x to the 3 minus 1. And I'm going to have y to the 2 minus 10. So I could write this as 2x squared y to the negative 8th. Or I could write this as 2x squared over y to the 8th. If this were a textbook problem, that's the answer that would be presented in the back of the book, for sure. If there's any way to get rid of negative signs in a problem, that's the choice the mathematician will make. But this is equivalent and correct. Personally, I don't care which answer you write.